Here is the counterintuitive truth about the deep ocean. The hard part is not reaching it. The hard part is making anything work there, twice, reliably, and with accountable data. Pressure rises by roughly 1 atmosphere every 10 meters of seawater. That simple gradient turns deep systems into pressure vessels, not ordinary machinery. At depth, you are also fighting corrosion, cold, turbidity, biofouling, and vibration. Then add multi-phase flow, sediment entrainment, and long gaps with no inspection. Even when something fails, recovery and repair can be impossible or delayed for months. So deep fluid engineering becomes a discipline of reliability, not heroics. Routine human labor at depth stays constrained by exposure, decompression risk, and rescue logistics. That pushes the workload onto robotics, remote instruments, and operational doctrine. Yet those machines must keep their seals, connectors, and sensors honest under combined stresses. Most qualification still tests one variable at a time in clean lab conditions. The open question is how to test pressure, corrosion, temperature, fouling, and vibration together. In the real ocean, they arrive as a bundle. A second big shift is that ocean mapping is being treated as a coordination problem. In 2018, the Nippon Foundation and JEBCO described Seabed 2030, a coordinated effort to map the world's oceans by 2030. That framing matters more than the slogan. It creates demand for scalable survey platforms, shared workflows, and interoperable bathymetric data. Without standards, deep mapping becomes a pile of incompatible missions and private data sets. With standards, it starts to look like infrastructure, something you can build upon. Metadata quality, uncertainty reporting, and repeat survey cadence become as important as the sonar. That also changes the vendor and lab ecosystem. Capability concentrates in ocean science, offshore energy, subsea robotics, environmental monitoring, and defense-adjacent maritime operations. Institutions like Woods Hole, MBARI, NOAA Ocean Exploration, JAMSTEC, IFREMA, and the UK National Oceanography Centre build platforms and operational know-how. Companies like Teledyne Marine, Kongsberg Maritime, Saab Oceaneering, and Sonodyne supply sensors, vehicles, navigation, and intervention tooling. Classification and assurance bodies, including DNV, ABS, and Bureau Veritas, shape what safe and qualified means. In deep fluids, governance is part of the stack, not an afterthought. A third finding is ecological, and it should change engineering requirements. A 2010 synthesis argued the deep ocean is large, diverse, and definitely different. It is not a uniform industrial volume of cold water. Pressure, temperature, darkness, chemical gradients, and substrate vary by location. So do the organisms and their sensitivity to disturbance. If you design tools as if everything down there is inert, you will over-damage habitats. You will also bias your own measurements by stirring sediment or contaminating samples. Ecology-aware doctrine becomes an engineering constraint, like fatigue limits or corrosion rates. That connects to a fourth shift, low-damage manipulation. In 2016, soft robotic grippers were demonstrated for biological sampling on deep reefs. The point is not novelty, it is compliance. A rigid industrial claw is great for valves and terrible for fragile organisms. Compliant, instrumented end effectors can reduce deformation and habitat disturbance. What is still missing are field metrics for damage, repeatability, cleaning, and contamination control. Once those metrics exist, low-disturbance interaction can become a procurement requirement, not a nice-to-have. A fifth and sobering insight is about contamination and accountability. In 2011, dispersants from the Deepwater Horizon incident were reported to have lingered in deep water. Deep fluids can store introduced chemicals and particulates for a long time. That changes the liability time profile of offshore and subsea operations. It also changes sensor strategy. You need long-duration monitoring packages, clear data custody rules, and governance triggers for remediation. Otherwise, out of sight becomes out of mind, even when effects persist. Now, zoom out to what makes deep fluid capability compound. It is not another one-off expedition vehicle. It is shared test infrastructure, calibration lineage, and failure reporting that travels across missions. Pressure-linked measurement discipline has been around for a long time, even dating back to 1894 tables for environmental measurement practice. The modern lesson is the same. If calibration and conversion are sloppy, your conclusions become politics, not evidence. If incident taxonomies are inconsistent, lessons do not transfer, and everyone repeats the same mistakes. Power and data are the other compounding layers. Persistent subsea observatories and monitoring stations need credible long-term energy. That links deep operations to grid flexibility, storage, offshore generation, and long-distance transmission concepts, including HVDC architectures. Without a power plan, subsea assets become disposable, not maintainable. And without data interoperability, digital twins and AI-driven monitoring become brittle automation, not resilient infrastructure. For strategy and capital allocation, the implication is straightforward.